Page 94, problem 44. So they tell us that the plane leaves from Chicago to LA at a given time, and another plane leaves from LA to Chicago 1 hour later. They tell us that the distance between the two cities is 1,800 miles. They give us the speeds of both planes. The one leaving from Chicago is 540 miles per hour. The one leaving from LA is 660 miles per hour. Now, the formulas or the equations formulas we're going to use are, the basic one is rate equals distance divided by time. For example, if you go 120 miles in 2 hours, your rate is 60. 120 divided by 2 is 60 miles per hour. Now from this equation, we can, if we multiply by the time, we can write it like this, right? Now, I'm going to set up sub-indexes for both planes. For the first plane, the one that leaves first, Chicago, let's call that, let's use sub-index 1. So this plane is going to be flying time 1 for distance d sub 1 at the rate r sub 1 equals 540 miles per hour. The second plane is going to be flying time sub 2 for a distance d sub 2 and rate r sub 2 equals 660 miles an hour. Now, the thing is, we are going to be measuring the times in both cases, time sub 2 for this plane and time sub 1, t sub 1 for this plane, is the flight time to meeting, to the point where they meet, somewhere here, we don't know. And a distance sub 2, distance sub 1 are the distances respectively for each plane up to the point where they meet. Now what else do we know? We know that this plane leaves 1 hour later. That means this plane, the second plane, is going to be on the air to the point of meeting 1 hour less. That's why I write t sub 2 equals t sub 1 minus 1. And then every time we are solving a word problem, we are looking for the hidden equality, because the hidden equality gives us the equation. Equation. So in this case, a hidden equality could be, for example, that the sum of the two distances flown by the planes to the meeting point equals 1800 miles. Because one plane leaves, the other one leaves from here, let's say they meet here, well, when you add the two distances, you get 1800. And then we have expressions for the distance using the main formula. The first distance equals first rate multiplied by the first time. The second distance equals rate 2 multiplied by the second time. So what we do is now, for the first distance, here we have the first distance. The second distance is here. I'm translating this equation here. I'm rewriting it here. So then you say, okay, we remember that the second time, let's go back here, equals the first time minus 1. So that's what I do, is I replace t sub 2 with t sub 1 minus 1. And now, as you can see, we have only one equation that has only one variable, the first time. So we solve it. I'm not going to get into the detail how to solve it, because you know how to do this. And let's see, 540 plus 660, yep, 1200 t sub 1 minus 660. And when you finish solving, you get the first time sub 1 is 2.05 hours. And the distance sub 1 is 1,107 miles. How do I find the distance? Because I plug it here, right? I say t equals 2.05 and r sub 1 equals 540. So I multiply the two and I get 1,107 miles. Now what is 2 hours? Well, if you want to go to minutes, you will see that it is 2 hours and 3 minutes. What you can do is multiply 0.05, the fraction part, by 60, and you will get exactly 3. And from there, once we know the first time, the second time is going to be 1 hour less than this, and the second distance is going to be 1800 minus this. And that's all about that problem. Okay, problem 46 is similar. We use the main formula as usual, rate equals distance over time. You have a mine exploding. By the way, you should pause the video and read the problem, because I don't have the text for the problem here on the screen, but you can read it. So you have a mine exploding at certain distance from the ship, and you are given the velocity of the sound in the air and in the water, and that allows you to solve the problem based on what? Well, based on the fact that distance in the water with capital D equals rate in the water multiplied by time in the water. Here it is. Distance in the air, small d, equals rate in the air with this velocity of the sound in the air multiplied by t. Now, what is the equality? Well, the equality again is in the fact that either you go through the water or through the air from the mine to the ship, the two distances are the same. So small d equals big D, and from here you solve the equation, you end up with this solution. Just follow the steps and you will see how you can get the answer. Problem 50. Problem 50 is you have two different solutions of sulfuric acid. One is 40%, the other one is 24%. You want to obtain a new solution at 30% concentration. So the question is, if you have 4 liters of 24% and you have a bunch of liters at 40%, how much should you use of this 40% mixing with this 24% to get 30%? Well, let's set up the equation. Let's follow the amount of acid that is being poured into the big container where we are going to create the new solution. If we use X liters of the 40%, then 0.4 times X is the amount of acid coming from this container. Since this solution is 24%, then 0.24 times 4, here it is the acid coming from this container. So 0.4x is acid coming from this container. 0.24 times 4 is acid coming from this container. It falls here, you mix it. At the end, what do you have? You have 4 liters came from here, X liters came from here, so you have 4 plus X liters, and the amount of acid is 30%. So the resulting acid is going to be 0.3 times 4 plus X. And now, what is the hidden equality? Well, the hidden equality, you say, well, the incoming acid equals resulting acid. That is, all the acid that came from these two is going to end up here. In other words, you make the assumption that you don't lose acid in the process, it doesn't evaporate, doesn't who knows what. So it's just all coming from here is here. So you set up the equation, you solve it, and you get X equals 2.4. So the answer is you must use 2.4 liters of 40%. On page 94, problem 62. So again, pause the video, read the problem, and see if you before trying to listen or watch the video, just read the problem. Okay, so you already read the problem, you know what this is about, and here there is a very interesting principle. Imagine, for example, that it takes you 2 hours to eat a pizza, and that you eat like a robot at the same speed. Your teeth chew the pizza at the same speed. You don't eat slower now and then faster. No, you always eat at the same speed. So if it takes you 2 hours to eat a pizza, in 1 hour you will eat 1/2 of the pizza, right? So the first hour, first half, second hour, second half. At the end of 2 hours, you have eaten the whole pizza. Now, suppose it takes you 3 hours. Then each hour you eat 1/3 of the pizza. Suppose it takes you 10 hours. Then each hour you eat 1/10 of the pizza. Notice how every time I flip the number. And that's a principle I'm going to be using here. If printer A prints the report in 3 hours, then that printer in 1 hour is going to print 1/3 of the report. If printer B prints the report in 4 hours, each hour is going to do 1/4 of the job. Now, both of them together, it takes them X hours. We don't know how much, so we say X. But using this principle, each hour, both of them together are going to do this fraction of the print job. Now, when you are doing this problem, you make several assumptions. First of all, the printers don't run out of ink, they keep working, they don't stop until they finish at the same time. And there are several assumptions that in real life they are not true, but we are simplifying the model here. So now, where is the hidden equality? The hidden equality is in the fact that the output per hour of both, which is this, equals the sum of the particular outputs of the particular printers. That is 1/x equals 1/3 plus 1/4. So you solve the problem, you get this, but remember, 1/x is how much both will print in 1 hour. You have to answer how long it takes. So you have to flip this, 12/7. And there you have the answer. Okay, quadratic equation, let's leave this for the next video.